Hello everyone. I am happy to introduce Professor Pramod Kumar Sharma, who is a professor of hydraulic engineering of the Department of Civil Engineering, IIT Roorkee, who has carried out enormous work in the field of hydraulics and water resources engineering. He did his PhD at the Indian Institute of Technology, Kanpur, and in the year 2004, he has been working with the IIT Roorkee nearly for 2 decades, who has done commendable work on surface nuclear magnetic resonance imaging. He has published a number of research papers. We are going to listen to him on the application part of the surface nuclear magnetic resonance imaging, which he has used recently in certain parts of northern India to understand and identify the subsurface hydrogeological conditions as well as groundwater occurrence. Happy to let us hear him today on the so we will hear him today on the application of surface nuclear magnetic resonance imaging. Thank you very much.
Good morning to everyone. I am going to start a lecture on the surface NMR for groundwater investigation. So, in recent years, the combination of non-invasive geophysical methods has become popular for the hydrogeophysical applications. The mostly this non-invasive geophysical methods that is nothing but that is used from the surface of the earth to directly measure the uh, earth properties below the surface of the earth. So in this regarding the ERT, that is the earth resistive tomography equipment, one is there. Another equipment is the surface NMR a geophysical method that can be used to categorize the subsurface soil media up to 100 meter from the surface of the soil. Okay. The geophysical exploration is nothing but this is the scientific measurement of physical properties of the Earth's crust by instrument located on the surface for investigation of groundwater. The estimation of these properties can be used for the assessment of production potential from aquifers, for the remediation and monitoring of contaminated sites, and for building predictive numerical models of surface flow. The, regarding this, one such property is of the aquifer is the mostly important, that is the hydraulic conductivity, which describes the ease with which the water flow in the subsurface media. Mostly conventional methods are also available to determine to compute the measure the hydraulic conductivity, which involves the drilling boreholes, installing wells, and conducting a hydraulic test for the various levels of the complexity. In this case, generally, we are taking the soil sample at different depth and taking in the lab and determining the uh, hydraulic conductivity. That is the conventional methods. The recently one method that is the which is most important, nuclear magnetic resonance, was developed by equipment. That is equipment name is the GM or ground magnetic resonance, which is basically work and the basic principle of the nuclear magnetic resonance, and was developed by Vista Clara USA. And this method is most cost-effective, high-resolution method, and for estimation of the hydraulic conductivity. So, in this case, the just you can see here, this is a glass of water, and water is made of chemical composition is the H2O. The H2O, and this is also based on the medical MRI, the medical resonance imaging. Okay, so this is the based on this principle. Medical MRI they are using to scan the body of the human body to see the different types of the disease or some fractures inside. Okay, so based on this nuclear magnetic resonance also working used in the geophysics. So from the surface of the earth, so generally we are keeping the wire loop on the surface of the earth, and it generates the magnetic field, and we send the signal to the water. In the water, there is the H2O, nuclear proton is there, and it will okay, so it will it will excite and it will send the signal to back to the equipment. Okay, so this is also used in the geophysics to characterize the different types of the aquifer material and finding the porosity, hydraulic conductivity, and water content. The first question is that what is the magnetic resonance? The magnetic resonance is a non-invasive physical method to directly detect the magnetic moment of hydrogen protons. Okay, a hydrogen proton is a spinning particle with a positive charge. Hence, it has a non-zero magnetic moment placed in a static magnetic field. The magnetic moment preferentially aligns in the direction of static field, and the magnetic moment precesses about the static field at frequency directly proportional to the static field strength. So this is the magnetic resonance. So uh, uh, so in this case, what happened? The hydrogen nucleus of the water or petroleum molecules has a magnetic moment, and it is aligned with the magnetic field of the earth. And this method utilizes the nuclear property of water or petroleum molecules. It is also possible to excite the hydrogen molecule by using an external magnetic field. After that, the signal responses can be measured from the precession of hydrogen protons when the external magnetic field is removed or switched off. It can also be observed that the surface NMR signals are directly related to the number of excited hydrogen protons. So this method can be used for the Earth's aquifer or rock for water content and the hydrological parameter estimation. So here, just you can see here, this is the basic principle of the ground magnetic resonance, which directly indicates the presence of groundwater based on the proton nuclear magnetic resonance. Okay, so in this case, proton of the hydrogen proton of the water molecule is already in the parallel to the Earth's magnetic field. Okay, the Earth's magnetic field is north to south. In that direction is also already in the static equilibrium condition. This is the equilibrium condition in there. They are in parallel to the Earth's magnetic field. Once this is the wire loop. The wire loop, once you introduce the extra magnetic field from this, and we are sending the pulse, then this hydrogen proton is exciting and it is changing the direction perpendicular to the Earth magnetic field. Okay, and after that, once the switch of this one, then it will try to come to the initial position and it will send the signal to the receiver. And this resonance, this response signals are stored in the receiver, and these signals are used in the further processing of the data through the inverse software is there, and from that software we are getting the output parameter for the just like a water content, hydraulic conductivity, and porosity, and water content for the for use of this aquifer material. Okay. And this is your water molecule, whatever I told in the previous slide. So this is your Earth magnetic field, and this is the parallel to the in equilibrium condition. After we are sending the extra magnetic field, this is the signals, And in that case, this is the water molecule is cited, and this is the coming to perpendicular to the Earth magnetic field, and it will send the signal in third to the receiver, and we are storing the signals and response, and we are then keeping for further processes. This is your geological material with the soil grain particles with the porous space filled with the water. And if I take this one, the small scale here, this is the square. And if I enlarge this one, you will get the four water molecules and soil grain particles. Okay. So in this case, whatever the signals are coming as we are receiving the signal response, so this is the NMR signal plotted with the signals and with time. So this is the exponentially decay, and this decay time is proportional to the pore space. So this is the long is coming. So it is depending upon the size of the pore space. If pore space is large, then we are getting the long decaying with time. But if space somewhere the pore space is small, then you will get the small response here. Small NMR signal will get the small here. So it will provide the water content, porosity, and pore size. From this we are getting. So here the relaxation time, this is your T1 and T2, this is the longitudinal, this is the transverse, this is the effective transverse, and you can be influenced by the magnetic geology. The surface NMR data acquisition, the depth of surface investigation is directly related to the shape and size of the cable loop. So first, we have to know at what depth we have to measure. So depending upon the depth of the aquifer, we will make the circular loop diameter by for a particular diameter according to depth of the investigation. The maximum area for a fixed cable length can be achieved by using the circular loop, and if sufficient surface area is not available at that site, then we are providing the square loop which can be used for the data acquisition. In the presence of electromagnetic noise, power lines, or any other noise source, we are using the 8 type of the loop, 8 type of the loops that can be used, which give the most accurate data. So once we are going for the site, we have to see some noise type of the power lines, buildings, okay, and we are based on depending upon the presence of noise in the field, we are selecting the 8 types, circular, square type of the loop here. A thumb rule is used for the surface NMR investigation and the shape of the loop here. Data acquisition in the GMR system is wholly based on the computer control. The quality of data depends on the input parameters and the accuracy of the auto-tuned frequency. So, for the resonance condition, the transmitted excited pulse frequency is almost equal to the Larmor frequency of the static earth magnetic field. The deviation of the station pulse frequencies should not be more than plus minus 3 Hz from the Larmor frequency here. For configuration of the cable loop, generally use circular, which give the signal best, and square give the moderate, figure 8 will give the poor here. For most investigation depth, it will give the circular depth best, but square will give the moderate, 8 type will give the poor here. So generally, if you are going for larger depth investigation, so mostly we are selecting the circular type of the loop, wire loop we are keeping, and we are getting the data. So here the T2 is the decay time. Once you are getting the decay time from the surface NMR based on the Larmor frequency of the Earth magnetic field. The different copper material can be classified based on the decay time here. So if the decay time is ranging from the 140 to 300, this is the it will indicate the fine sand. If the 90 to 492.9, it will give the medium sand, and this is the 140 to 80, it will give the coarse sand here. So just you can see here, this is the basic use of earth field as a background field, a larger surface called for NMR extraction, and this is the your our GMR equipment, ground magnetic resonance. The name of the equipment is GMR, which work on the principle of the surface NMR. Okay, this is the laptop, and this is the this is the one circular loop. This is the water molecule. In equilibrium condition, just you can see here the earth magnetic field that is equal to the your magnetic field of the earth, and moment that is proportional to the volt multiplied by the earth magnetic field of the volt of the H2O. So once through the circular review, if you are sending the signal, which automatic generate the magnetic field. This magnetic field will go to send the signal, and it will excite the hydrogen molecule, and the Larmor frequency can be obtained from this expression. The gamma represents the gravimetric ratio by 2 pi B naught the earth magnetic field, and this will give the frequency 1500 to 3000 between the range. 1500 to 3000. In between, it will show the your Larmor value of the Larmor frequency. Once it will process, then the receiver will receive the signals, and it will store in the receiver. And you will see the here decay type of the NMR signal will, or voltage of the NMR signal will, it will show the with respect to time here, excitation pulse here. This is the moment of the magnetic field here. It can be obtained here. This is the depth sensitivity. If the depth is very large, in the previous slide, here this is the small depth, and if you are going this is the small with respect to small decaying with response of the NMR signal. If you are going the larger depth, you will get the larger long decay type of the curve here. Here, the water molecule, water is available in the larger depth in the aquifer from the surface of the earth. Then you will receive the decay type of the excitation pulse large here. This is the moment depth resistivity. The B1 component transfers to B naught exert a torque causing M to tip into transverse plane here. So, and the theta angle can be net tip angle are determined by B1. So this expression can be used here. And the maximum transverse magnetization and signal M0 theta is 90 degree. It will give the M0 sin theta. Even the theta is 180 degree, no signal can be obtained here. This is a single pulse provides certain sensitivity. So if the depth is small, they will get this type of the signal here, and here Q can be obtained from the current into time pulse, and this is the for a small depth Q is 500 ampere millisecond, and this is the medium. This is 1600. At 100 meter, you will get the 5000 ampere millisecond. If you provide we plot the curve here, pulse moment Q. So Q is nothing but it will give the depth of the aquifer. Depth of the aquifer here. So here you can see the sounding curve. How can you obtain the sounding curve? Pulse moment Q, AS, and NMR amplitude nanovolt here. For a shallow aquifer, if I go to the shallow aquifer and if I plot the sounding curve, it will give the green color here. This type of the curve you will obtain here. If I go the deep aquifer, this is the red color, you will get this type of the curve here. And if I go the combination of shallow aquifer and deep aquifer, you will get the high magnitude of the NMR amplitude, you will get the high peak curve with combination of shallow aquifer and deep aquifer. This is the this is the difference in the peak of the shallow, deep, and combination of shallow and deep aquifer. You can obtain the with respect to amplitude of the nanovolt or sounding curve with respect to the pulse moment Q. Collecting a complete GMR data set. So once you are starting the GMR in the field, you have to give the different type of the stacks. So it will the basic idea behind the stack is that so to get the more accurate data in terms of the response of the NMR, you are going to the minimum eight you are generally using, and but eight if you are using, so you will get the some less accurate data response data. But you are using the 16, depending upon the site condition. If there is no noise type of the there is no noise at the site, it will give the 8 in terms of 8 stack, it will give the 8 stack data correct. Otherwise, you have to go to the 32, 50, up to 50, 100 also stack to correct the data. And this just you can see here Q1 and Q2, Q3, Q4 is the stack 1. The stack 1, this is the stack 2 here, this is the stack 3. In that way, it will go for the tier 4 to 8 seconds. One stack time will take to 4 to 12 minutes. So when the field, it will take for one side collection of the data, it will take 4 to 5 hours. This is the adapted noise cancellation in multi-channel. This is the your this is the your GMR equipment. This is the 8 type of the loop detection loop here, and this is the power lines is their noise source. In that case, you have to use the red cable circular type to remove the noise cancellation here. Okay. This is the 2D geometry, 8 type overlapping you are using for 2D, and this is the for 1D you are using. The always says the noise cancellation performance dynamically in the field. If not achieved good, noise cancellation stop and try new coil strategy. Stacking is much less efficient than noise cancellation. Fixing noise coils can give factor of 10 improvement in the SNR, surface NMR resonance. To get same factor by stacking would need to stack 100 times longer. So basically, once we are in the field, what we are doing here after collecting the data, one stack, two stack, three stack, four stack, that is data we are using for the checking the accuracy. So parallel we are also checking the accuracy of the data. If data is not good, then again we are changing the site condition, or we are using the extra noise cancellation loop in the field to get the most accurate resonance data here. Based on that, we are doing the experiment here. The main component of the GMR hardware component is that this is the DC converter, and this is the multi-channel transmitter, and this is the tuning capacitance. Okay. And selecting the survey parameter, this is the first we are using the loop size. After that, you are calculating the frequency, tuning capacitance. So you are going for the auto tune. In auto tune, it will give the equipment, will give the capacitance value. Based on that, we are changing the here capacitance. The minimum is 0.5 and 15.5 here maximum. So after auto tune, whatever you are getting the value of capacitance, we are opening this box and we are changing the capacitor, that value. In the field, it will come 1.5, 2.5, 4.5, yeah, 0.5, depending upon the site, what is the frequency, LMR frequency. Okay. So we have to give this one. What is the magnetic field that? After that, we have to use the pulse length, pulse moment sampling, and types of the pulse sequence you are using here. Loop size, the maximum investigation depth, loop diameter. The typical loop size 20 to 100 meter can be used here. So if you're using the 100-meter loop in the field, it will give the 1.5 times of the diameter of the loop. The 100-meter, it means that 150-meter vertically, 1D, it will give the uh, data and it will get the water distribution on hydraulic conductivity you can find. But if you are for a single loop, you can go circle. Single loop, you can loop. If you are using the small loop, just like a 10 meter, 20 meter, 30 meter, the way to use the 3 to 4 turn and to increase the here. The for loop is smaller than 50 meter, use the multiple runs here turns. Loop shape, choose loop shape that is easy to lay out. Most easily that circular type of the loop can be used with no obstacles. The square exists for big loops and tree area. So when the in garden or tree are available, in that case we are using for the square types of the loop. Loop size and shape may be constrained by available area and noise sources. Generally what happened at that site, you are giving the latitude and longitude for this, you are going to that site, this NOAA site here. From that NOAA site, you are estimating the Earth magnetic field here, nanotesla. So once you are starting the GMR equipment in the, or doing the experiment in the field, so first of all, for that place, you have to calculate find the latitude and longitude. And after that, finding this one, you are going to this site and you are putting this site and you are calculating the total Earth magnetic field. And this Earth magnetic field we are giving in the auto tune in laptop in software, and it will give the automatic frequency. It will automatically calculate the frequency. Or you can also, once you calculate this one, you can calculate from this expression also here directly can be calculated. For the root key, we are finding the 2073 hertz. This is the LMR frequency, and after auto tuning, you are going the final software for collection data. You are giving this data, this value, and Earth magnetic field, and based on the other parameter also giving and starting to collect collection of the data here. This is the GM Auto Tune software. This is the frequency, and this is the alarm frequency, and this is the current frequency. You will get this type of the curve, and adjust auto tune. It will give from this one you can calculate here. Selecting a pulse length, a default pulse length, you are using 20 millisecond. If you are getting the small, then your time will increase. Shorter pulse length, it will increase the time. Okay. The longer pulse length, 42 to 80, also allow for the total pulse moment and deeper imaging. Shorter pulse allow detection of the shorter NMR signals here. So this is the one site in near Roorkee. He did the experiment at that site by using this GMR equipment. This is the battery. Okay, and this is your main receiver unit here. This is the tuning, and this is the GMR equipment. Okay, and this is the yellow line is the main wire loop here. This is the detection loop, and this yellow wire is the noise loop here. You are keeping here, and you are starting by managing this one. So there is also guidelines at what point you have to keep the laptop from the main equipment because it will generate the very high frequency. So once you are starting this experiment near the site area, this near the loop, you are not allowing the mm, any person to move in the site or any animals like cow or any animals. Okay. And only we can also observe that there is no birds also not coming nearby this area because of generation of high frequency during the experimentation and also generate high voltage. So, so after processing of the data, collection of data, you are getting the decay time distribution with that. Okay. And you are getting the water content. This is the 1D mobile. This is the this 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 one is showing the your mobile water, and this is the pink color is showing the immobile water. So whatever this water is there, that cannot move, but this water is moved that can easily move here. And this line will give the water table. So this is the 4 meter is the water table, and this equipment does not work in case of unsaturated porous media. So this will give the only the data for the saturated porous media where the water is available. Water molecules are there, water is available. So once you identify from this also you can easily identify the water table, or some manually you can find the water table at that site by digging out this one, okay, or you can by see the well nearby that site you can identify the water table. Based on that you can mark the line here, and this is the hydraulic conductivity variation. Okay, and in this case, what happened? We have uh, um, taken the hydraulic conductivity from the NMR equipment, and also estimated the uh, hydraulic conductivity by different empirical equations by Kozny, Karman, Tarjigi, Hajan, Slicha, Kroger, and Jamrian. Okay, and you are finding that you have shown that the behavior of hydraulic conductivity, whatever the data is there, they are all already matching to the all this equation. The bulk condition of mobile bound water content, unsaturated, saturated conductivity of aquifer, comparison of hydraulic conductivity using the surface and original empirical equation. The estimated aquifer hydraulic conductivity pattern was almost similar to the observed surface NMR hydraulic conductivity, and the error of the modified equation was also in an acceptable range. The findings of the presentation might be useful for predicting the subsurface property at other sites with similar geological conditions here. So this is also based on that ERT also working. The best method is that working using of this equipment is that at one point use the equipment, collect the data, and calibrate with the other data available from the field site by other method, conventional method. After comparison of that calibration of this one, calibrate, and you can use the equipment for other places. One site you can give the calibration, other site you can find that one. It will give the much more accurate data of the variation of hydraulic conductivity and water content here in that way. Basically, this is working based on the principle of the Earth magnetic field available in the uh, so after all, this is an estimate of the bound water, that is the free mobile water, and total NMR detected water content as a function of depth. Water table occurs at here. Other site also we work here. This is the almost other site where This is the here 6 meter water table is there. Just you can see here 6 meter. The 6 meter below ground surface, the water content each depth interval is sorted into a continuous distribution of water content. That is the T2 star decay ratio, decay rate here. The cutoff T2 is 30 milliseconds used to segregate then bound water. T2 is less than 30 milliseconds from free water content. T2 is greater than 30 milliseconds. The second graph shows the water content percentage graph in T2 decay rate, which is greater than the 33 millisecond will be calibrated mobile, and graph which is less than 33 millisecond called the immobile water. For the mobile graph, color is light greenish. On mobile graph, color is pink color, and black show the total water content. Black line colors hydraulic variation. Here it means that the black line show the total water content. This is the your variation, and this is the hydraulic conductivity variation. Here you can see the below the above the water table. This is the unsaturated up to 6 meter around. This is the unsaturated media. It hydraulic conductivity not showing correct here. Okay, and below the groundwater table or table, this is the variation hydraulic conductivity. It is showing here. This is the all about the basic principles and findings of the some site here. The surface environment are not intended for the urban or suburban environments. Avoid noise sources, power lines, buildings, motors, electronics, electric trains, and your wire mesh. These noise sources, in the presence of these noise sources, this equipment will not give the accurate result here. So once we are using this equipment, we are avoiding these noise sources, then it will give the good results. Okay, thank you.